Hey there, are you ready to wrap up modular arithmetic? This video is going to get into one of my favorite areas, and that is cryptography. For a little while there in college, I thought seriously about being one of those cryptanalysts in like the CIA or something, but life did not take me that direction, but that's all right. But let's just do a small exposure to the history of cryptography and how it relates to modular arithmetic. You're going to learn about a few people here that'll be important in your mathematician list and learn some cool stuff. Some of it you might be familiar with if you've ever bought Cracker Jacks and gotten a secret decoder ring. Some of this you might have seen before. Anyhow, let's do this. So what is cryptography? It's actually derived from the Greek kryptos, meaning hidden, and graphine, meaning to write. So it literally means hidden writing. It's got numerous applications because, besides the obvious, you can send secret messages that make sure only the person on the other end knows what's being said. But this applies in your lives nowadays, like with your cell phones, your emails, your Wi-Fi, and using like the smart devices in your home, those kinds of things. You're counting on cryptography to keep your data safe. Whenever you do your online banking or use any of these apps, you're relying on the messages back and forth being something that's only you and the intended recipient knows what's going on. So the message being sent in cryptography is called the plain text, and then the code is called the ciphertext. So when you put a plain text message into secret code, you're encrypting it, and then it is now in ciphertext. And then on the other end, the intended recipient should be able to take the ciphertext and decode it back into the plain text for their use. And you can go back and forth this way. Okay. One of the early examples of this was the Caesar cipher. And this is the one that, if you've ever done one of those like secret decoder rings or anything, or in the cereal boxes or whatnot, it's basically a form of the Caesar cipher. That goes all the way back to Roman Emperor Julius Caesar. And he did this around 50 BC. He would write to Cicero using this cipher. Basically, each letter would be replaced by a letter that occurs 3 places down in the alphabet. And then Cicero on the other end knew to reverse it by 3 letters in order to decrypt the message. So in our alphabet, how would that work? Well, we have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. 26 letters. Q, R, S, T, U, V, W, X, Y, Z. So then if you go 3 letters down, this would be the original plain text. Then the ciphertext would be on the other side of that. You'd go 3 letters down, so the ciphertext for A would be D. And you guys pick up from here. D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C. So even though Z is at the end of the alphabet, like starting at X, you would cycle back around to A. So X, the plain text X would become the ciphertext C. So the ciphertext is the one on the right side. So let's say you wanted to write a message like, Caesar was great. You'd have to go back to your plain text. And okay, so the plain text C would translate to F in ciphertext. The plain text A would translate to D in ciphertext. E would become H. S would become V. A would be, again, D. R would be U. You could leave a space for the space if you want. W would be Z. A would be the D. S would be V, space, G would become J, R would become the U, E would become H, A again D, T would become W. So Cicero would receive that mess of letters. And the hope was, as the runner was taking this message from Caesar to Cicero, the runner wouldn't know what it said, and then if somebody intercepted the runner, they wouldn't know what it said. Just Cicero would be able to take it and decipher what it was saying. Because it looks like a mess of letters. But if any of you have ever done those puzzles in the newspaper with the letters, I think they're called like cryptoquotes or something, you start to quickly see that there's patterns that you can work out. There's certain letters that appear the most often in the alphabet. You can start making some guesses and replacements, and eventually things kind of fall into place. It's a little too easy to break. And for that reason, it wasn't used too long by Caesar. And he also didn't trust Cicero, but anyhow. But he would send that message. Cicero would get it, and then Cicero would know to go the other direction from ciphertext to plaintext. So he'd get the F, and he'd know to go from F back to C. He'd get the D, and he'd know to go back to A, and so on. And you could say, oh, Caesar's, talking about himself again. He was great. What does he mean by was? He still is. What's going on here? Yeah. Anyways. So that was like an early form of trying to do cryptology. The message we have here, I know we did it all in letters, but of course it's math class, so with math comes numbers. And you can take the alphabet and you can assign numbers to the letters. Like A, you can assign 0, 1, B, you can assign 0, 2, C, 0, 3, and so on, all the way down to Z, which would be 26. So if you want to further make this, kind of interesting, you could take Caesar was great and you could write it in numbers, the encrypted message in numbers instead of letters. So that would be another way to add a little bit of complexity to it. So let's see here. So F would translate to 6, D would translate to 4, H would translate to 8, V would translate to 22, D would translate to 4, and U would translate to 21. So you could send that string of numbers. Z would be 26, D would be 4, V would be 22. And then you had J would be 10, U would be 21, H would be 8, D would be 4, W would be 23. And then he would know what those numbers matched up with, what letters, and then he could take the letters and go backwards and figure out the message. He could also use modular arithmetic. If the numbers for the plain text are P and the numbers for the ciphertext are C, he could use one of these two equations, congruences, to go back and forth between the numbers, like to decipher or encipher if he wanted to. Like for the word Caesar. All right, so we know Caesar would be 3, 1, 5, 19, 1, and 18. So if you wanted to take that plain text, P, these numbers would go in for P. So like, let's say you wanted to take that first number, 3, and you wanted to figure out what ciphertext number that would go with. He could say C is congruent to 3 plus 3 mod 26. So C is congruent to 6 mod 26. So you could say that C should be encoded as, the C should be 6. So if you put a 6 there as your ciphertext, and you could do that for each of those numbers. Basically, you're adding 3 because you're going 3 letters down in the alphabet. And if you were trying to take Z, like if you had Z, Oh no, well, let's see here. What's a good one? Yeah, let's do Z, which is 26. Like if you were trying to encrypt that, you would have C is congruent to 26 plus 3 mod 26. So you'd end up with C is congruent to 29, which is also congruent to 3 mod 26. And you could work with that. Now if you want to go the other direction, if you want to take the ciphertext and take it back to plain text, you could use the second congruence. P is congruent to, so we can take that 6 minus 3 mod 26. So that would be another way to do it. Or you could do P is congruent to 6 plus 23 mod 26. Either one will work. This first one comes out to 3 mod 26. But so does that second one, 29, which is also congruent to 3 mod 26. So yeah, you could actually use congruent statements to go back and forth if you wanted to use the numerical version of the letters. So that's something that you can do to make it a little extra complicated. Or, like in today's terms, your computers do well with numbers, so you could set up a formula or an equation to have your computer work this out for you. Obviously, we did not stick around using this forever because Caesar quit using this soon after starting because of how easy it is to break and because he didn't trust Cicero. Cicero had the key, and you have to trust the bearer of the key, otherwise it's going to break down and not work. But fast forward lots and lots of years. Over time, in World War II, we had the introduction of computers. And I'm going to briefly touch on that in a few minutes. That with computers comes great potential as far as communications, but also comes with a great need to decipher things. And in fact, the first computers, which we didn't realize were invented until later because it was classified military documents, but the first computer was invented during World War II by Tommy Flowers with the help of Alan Turing. And they invented the computer to try to break German codes. Germans were sending their messages over the airwaves, not just in Morse code, but also encrypted. And we were trying to figure out how. So they invented the first computers to do that. But I'll get back to that in a minute. But over time, the encryption methods have had to get far more complex because as computers get better and faster, these codes can get broken faster and faster. And more recently, there was something called the RSA system. And I wanted to briefly expose you to that because it'll show you how primes and stuff are used now in encryption too. This RSA system's named for Rivest, Shamir, and Adelman. They proposed this in 1977, so this was before many of you were born. At the time, their system was unbreakable due to the use of the product of two large prime numbers as an enciphering modulus. Alright, I briefly mentioned this in a previous video, how it's hard to, like when you're doing prime factorization, if you have a really large number, it can be hard to break it down to its prime factors. But if your really large number only has two prime number factors, it can be super hard to break it down. And that's the point that they used to help them with creating this system. It was virtually unbreakable. It was unbreakable at the time. But they used two very large prime numbers and multiplied them together and then used that product for their enciphering modulus. And as of 1998, this system was still basically unbreakable. A single computer would have taken 3,800,000,000 years to find the enciphering modulus. So at the time, it's like, well, that's not going to happen. So it's pretty safe, it's a pretty secure system. But that's a single computer. If you start networking computers, that speeds up a lot faster. So then it becomes more doable to break. In 1977, when they invented this system, this RSA 129, they submitted a message to Scientific American. You're probably not familiar with Scientific American, but they often have magazines and stuff. But they submitted a message to them, and the message they sent would have taken, at the time, the fastest computer, not thousands or millions or billions or trillions, but 40 quadrillion years to try to decipher it. Let that sink in. In 40 quadrillion years, our Earth's not going to be here anymore. Our universe, our Milky Way won't be here anymore, I'm sure. That's way down the road, so like that seemed pretty secure, you know? But as time went on and as things got better, computers, it wasn't so secure anymore. In 1994, a network of 1,600 computers broke it within 8 months. So we went from 40 quadrillion years to 8 months to actually break it. So then it became useless. Can't have that happening. So more and more systems had to get developed over time. The systems they use now are not, they don't use RSA 129 now. They use other types of cryptography systems, but it's just kind of an interesting thing as it's grown and as computers have developed, how computers can respond and then how people have had to respond in kind. With that said, I wanted to kind of show you how that RSA system works with something a little simpler. Now, by the way, the message they sent when they sent that message to the Scientific American, the message was, the magic words are squeamish ossifrage. Of course, Scientific American didn't know that because at the time they couldn't break it and figure out what was being said, but now we know. Very strange statement, huh? But not something somebody's going to guess easily. Probably not going to guess the word squeamish or the word ossifrage easily, so I made sure it's kind of a weird message to begin with. Alright, anyways, let's take a look. Let's not try to encode that message. Let's take the message no way. And let's see how we would encrypt that using the RSA system. Alright, and for our purposes, we're going to use 2 small primes. RSA system would use 2 ginormous primes. We're not going to do that. We're going to use 29 to stand in for P, and we're going to use 53 to stand in for Q. So 29 and 53 are both prime numbers. The enciphering modulus in is found by doing 29 times 53. So you get 1,537. Phi of n uses n minus 1 or p minus 1 times q minus 1. So 28 times 52 is 1,456. We need to find the greatest common divisor of some number in the 1,456 to equal 1. So this 1,456 we just found for phi of n. We need to figure out what number in that would have a greatest common divisor of 1. In other words, what number is relatively prime with 1,456? And that number happens to be 47. So k equals 47 is going to be our enciphering exponent. Then they need a recovery exponent. So kj, and figure out, remember we had k there is 47. Kj has to be congruent to 1 mod phi of n. So 47 times j has to be congruent to 1 mod 1,456. So j would have to be 31 to make that happen. All right. Now to encipher the message. Remember how we had before, how we took like A and made it 1, B made it 2, C made it 3, and so on? We can do the same thing with this message. No way would come out to 14, 15, then we'll go ahead and use 0, 0 for the space, 23, 1, and 25. So N is the 14th letter in the alphabet, O is the 15th letter in the alphabet, empty space is 0, 0, W is the 23rd letter in the alphabet, A is the 1st, Y is the 25th. So we just put ahead and put that into numbers. And then we're going to break that up into these little groups. We're going to group, we're going to break it up into groups of 3. Right there. And we're going to use that enciphering exponent from earlier. Enciphering means you're putting it into code. So we're going to take 141 and raise it to the 47th power. And then figure out what that's congruent to mod 1537. So right now it's all about encrypting. So the enciphering modulus, 1537. That's why it's mod 1537. The 141 comes from the letters, the beginning of no way. And then the enciphering exponent is the 47. So you figure out what that is, you work it out. For the other numbers, it's like 500 to the 47th power is congruent to what? Mod 1537. And so on. 230 to the 47th power. 125 to the 47th power. And you're trying to figure out what those are congruent to. And you could start putting it in your calculator, but you're going to notice your calculator is going to get really cranky. Because not only does it not want to do the 47th power, but then you're trying to figure out what the remainder would be when you divide by 1537. It's going to get cranky. But the computer system can work it out and would get, I'll do it in a different color, we'll get 658 for this one. We'll get 1408 for this one. We get 1250 for this one. And we get 1252 for that one. So then you would send 0658 1408 1250 1252. So that's what you would send in order to communicate no way, but being encrypted. The person on the receiving end would take what they just got and use the recovery exponent. Up here, this recovery exponent of 31, that J, they would use that. They would take the 658 they just got, raise that to the 31st power, figure out what that's congruent to mod 1537. They don't even have to know what the enciphering exponent is, which is a good thing. They don't have to know anything about how it was enciphered. They just need to know how to decipher it. So that helps add an extra layer of security. So if the message gets intercepted in between, the only ones that know how it was enciphered were the ones that did the enciphering. You could take the 1408, raise to the 31st power, see what that's congruent to. The 1250, raise to the 31st power, and the 1252, raise to the 31st power. All that would be mod 1537 still. Enciphering modulus there. And if they work it out, they would get, let's use a different color. I like colors. They would get 141 here. They would get 500 here. They would get 230 here. They get 125 here. Which should look familiar. So you go back up. There's your 141. There's your 500, your 230, and your 125. So it would bring you right back to those numbers. And then they would know how that all matches up in the string to the letters. way. But yeah, that's how that would work. So get an idea. I mean, you don't have to know how to do that for a test or anything. I just wanted to give you an idea about how the system works generally and give you a real appreciation for how difficult it would be to break it on your own. And back then, computers were so much slower. So just give you an appreciation for where that system was back in 1977. So back, 43 years ago. But obviously it didn't last for long, because I talked about how in 1994 computers were able to break the code in 8 months. So the National Institute for Standardization and Technology started a contest in 1997 to try to find a new reliable way to secure data. Something called the Ryandale block cipher came about. It uses multiple areas of mathematics, not just primes and modular arithmetic. That was selected as the winner in October of 2000. And these kinds of processes are not always quick, so it took 3 years for it to be presented, be brought about, presented, and vetted, and then implemented. Officially became the encryption standard in May of 2002. They actually call it the advanced encryption standard. So it got updated a little bit. So the Ryandale cipher, with some updates, became the advanced encryption standard. The our U.S. government was using it for information that was not classified. But then in 2003, they're like, actually we were using it for classified data too. They didn't want to tell people that, but they were. It's impossible to do direct break, like just now, like when we were doing the RSA system. It's impossible to try to guess on your own without like some kind of supercomputer's help what those prime numbers are that are being used. And with this more advanced system, those keys are impossible to break directly, but there's something called side channel attacks. When you start getting very complex algorithms and complicated programs, the algorithm itself can be secure, but sometimes the way you're implementing it in the computer system can leak certain kinds of information that would weaken the system, and they call it side channel attacks. More algorithms came about because, things are starting to move at lightning speed in the 2000s as far as technology, computers, speed, and all that. So by 2011, there was something called the secure hash algorithm that had been in use. Like, they graduated from Ryandale. And all of a sudden they couldn't use that anymore because an associate professor, Wang, I don't know how to say her last name, I think it's Zhao Yun, she cracked it. And it's kind of funny because if that link as a news story to it. I had another link previously on my slides that took you to another news story, but that one's been taken down. That website's been taken down. But it's kind of funny because she commented on how she was so excited the morning that she cracked it, and then she felt so relaxed, felt at peace and ease and relaxed. After trying to work on this problem for so long, and then finally finding the solution, she just felt pleasant, and just kind of went out and drank some tea and relaxed and all of that. And at the same time, it's kind of pleasing because she had broken something and knew the secret that nobody else in the world knew now, nobody knew she had done it yet. So it was kind of a little, almost like a little private joke for a little while until she told everybody what she'd done. So if you're more interested in that story, you can go to that link and check out more about her. I have not done any further research to see what's being done as of 2020, because obviously 2011 was 9 years ago, and a lot has changed in the last 9 years. If you want to do some research and share it with me, that would be pretty cool. Maybe it can be worth some bonus points, because then I can update my slides here. That would be pretty neat if you found some decent information that I could share with the class about data security. Cryptography in World War II. As I mentioned earlier, the first computers came about because we were trying to break codes, and that was during World War II. The Germans used something called the Enigma machine. Pretty cool. You can go on, I think, eBay. You can search for an Enigma machine, and you can actually buy one. But it wasn't a computer. It was a machine, mechanical machine. It had these rotors, modular 26 system, 4 rotors with 26 letters each. So it was the German alphabet, but still. So the 26 letters were on each rotor, and 4 rotors. And then they would set the rotors a certain way each day. and then the machine would be able to use those settings to encrypt the messages that the Germans were sending. And then the people on the other end receiving the messages, they would know those settings, be able to set their machines so that they could decrypt the message. It was really difficult to break. If you think about 26 to the 4th power, that's a lot of variations it has to go through before being encrypted. And we had some of the best and brightest minds at a mansion called Bletchley Park in England. And then we also had some of the best and brightest minds here in the US too, all staying in one place, all trying to work on deciphering these messages. Eventually, the system broke because the French Secret Service were able to obtain some wiring instructions, share them with the Allies, and then that allowed them to figure out just how the machine was being wired to be able to start breaking the codes. And then mathematicians had to know how to apply the mathematics to setting up the machine and breaking the codes too. So group theory. Remember we talked a little bit about the groups last, I think 2 videos ago? Well, group theory helps save us. If you'd like to know more about this, you can look up Bletchley Park and find a ton of information. There's an old movie called Decoding Nazi Secrets that used to be in Polk State Library, but that was back in VHS tape days. I don't know if it's available nowadays online or not. But more recently, big Hollywood movie, The Imitation Game, had Benedict Cumberbatch playing Alan Turing. Awesome movie, tells you the story there of what was going on with Bletchley Park. But the 2 key players were Alan Turing and Tommy Flowers. Tommy Flowers designed Colossus, an early electronic computer that helped break these ciphers, worked with Turing at Bletchley Park, who became known as the father of modern computer science. So those are 2 characters that you also want to add to your mathematician list. And then at the very end here, I have a slide on Emmy Noether. It's a little out of place. I should probably have moved it back to when we were doing the groups. But she was a big mathematician right before the World War II era. And Albert Einstein knew about her and her work. And that's significant because Albert Einstein also, his research went on to help with developing the atomic bomb and so forth. But just a little bit about her. She was very talented abstract algebraist. So all that group theory stuff, when we talked about groups with the modular arithmetic, with the addition, with the first video that we did for this unit, she worked extensively with abstract algebra in those groups. And when I say group theory won the war, like much of her work was what helped those mathematicians know what they were doing in World War II. She was German, and she was never granted a regular professorship there because simply she was a woman. That was an era where women weren't allowed those kinds of things, and not just in Germany, but all over. In 1933, she was able to come to the U.S., and here she was able to actually get a faculty appointment. 1933. Unfortunately, 2 years later, she suddenly passed away when she had surgery for a large ovarian cyst and then had complications from that surgery. Really sad, tragic loss because she was one of the most creative abstract algebraists of modern times, in the words of Albert Einstein. So I want to add her to your mathematician list too. All right, well, I think that's all that I want to go on about with cryptography. You can take entire courses and do entire studies on cryptography, so obviously I can't do all that right now in this one video. I just wanted to give you a little taste of it and show you how some of the early versions are, how the roots are in the type of math that we are doing here with the congruences and the modular arithmetic. So, hope that you enjoyed this little journey. Don't forget to update your mathematician list, and don't forget to check out all the other links and documents that are in the module for this unit. Have a great day, and I'll see you in the next unit.